starting to record. There we go. Oh, okay, I see. Yeah, pictures can work. Yep, you can certainly use a picture. It's just harder for a picture to kind of keep track of what is in queue and what is not in queue. So you kind of have to mark something and then cross it out, and then mark something else and then cross it out. But it can be done. It's or you can do an animation style, right? You can basically, if you're doing this on a computer, you can also do it in animation style. So you can basically just have different frames, each one representing what happens in one iteration of the while loop. That can be interesting because if you did that, then you would probably see the expansion of the vertices based on the known distance to a destination vertex. So that can be interesting. I'm not that much of a visual person when it comes to understanding algorithms and stuff like that. All right. Well, we still have about a minute to go. Oh, okay. Yeah. Yep, we all learn differently. Some people are audible learners, and I'm terrible when something is just audible, when something is just when they're just words. Um, I mean, I can listen to a radio drama or something like that, but I can't really listen to anything that's abstract and just use the audible source or medium to understand the concepts. I'm kind of more of a definition kind of person. I have to look at the definition and find out, how the definitions relate to each other, and then just do it a few times, practice a few times, and then kind of have an internal representation of all those concepts in my head. So anyway, I'm showing what you're seeing here is Joplin, and to be more specific, I am writing some material. I wouldn't call it a book, okay, but I'm writing some material on abstract and critical thinking. It's more or less a note to self, to basically summarize what I know about abstract and critical thinking. Some of this has to do with me kind of looking at the way that I think and then try to document that. So anyway, that's also what I'm using Joplin for. And I find Joplin is a pretty useful resource just because it's easy to type, and also it's pretty easy to visualize what I have typed. I cannot do Canvas, the HTML editor of Canvas. That's kind of opposite to what I really would like to use, because I don't want to use the mouse. Every single time I need to change a font to something else, I have to use a mouse, use a mouse, change the font of particular words. And on the background, that's just a lot of extra work that I don't want to do. So anyway, it is time to start the class, and I'm starting. So for the most part, we are really done. Not for the most part, we are done with the A-star algorithm, as well as Dijkstra's algorithm. So you have a new homework assignment that is based on the A-star algorithm. We did a trace last week already, so that's kind of what we are going to talk about in terms of graphs and the two algorithms to find shortest paths for graphs. Do we have any questions about graphs in general, or any questions about the two algorithms that we have talked about? One is Dijkstra's algorithm, the other one is the A-star algorithm. So we got some text coming in. All right. I do that a lot. You're having a question and then you totally forget about it quickly. How many such algorithms are there? I'm not sure what you mean by such algorithms. So if you're talking about algorithms that can find a shortest path, there are variants. Okay, there are variations of the A-star algorithm. I talked about the C-star algorithm before. It is a recursive, successive, deepening type of algorithm. So it doesn't really do any type of loop detection, like like what you have to do if you have a depth first search algorithm. So C star is interesting because you can basically, if you have a hard time limit, okay, in other words, you have a robotic application, and you kind of have to decide what you need to do before you get to a point where you can make a left turn or go straight. Okay. So during the time to get to that destination, well, I mean, you can run a few iterations of the C star algorithm, and then whatever is giving you, whatever is the deepest, that's informing you, okay, we should probably take this route or take the other route. You just make a decision. Okay, it may not be optimal, it may not be the optimal path, but given the amount of time that you have, that's the best decision you can make at that point. So the C star algorithm is kind of an interesting spin of the A star algorithm, because the C star algorithm usually also make use of heuristics. Okay, so can we go over the homework? Yeah, sure. And then we have, in Dijkstra's algorithm, the line says select V in Q such that it has the smallest L of V, and it makes the algorithm greedy. Yes. So remember what I said. Greedy is not a very good description, because I think it's more like optimistic. The optimistic part meaning, if you find a vertex that has the shortest that has the shortest path to a destination already, you're kind of banking on the fact that if other vertices can also get to this particular vertex, those vertices stand a pretty good chance of using this vertex as a through vertex to a destination vertex. So I see it more like optimism rather than greed. But I suppose the people who coined this type of algorithm use the word greedy to describe these algorithms. But Armand is correct. That is why it is called a greedy algorithm. All right. So since are there other types of algorithms like greedy, and can we change that line to make Dijkstra into something else that is not greedy? That is a good question. That is a good question. I think you can potentially make the wrong choice when you're choosing a vertex to expand out of Q, and it would still be able to find the shortest path, as long as the decision-making part, the conditional statement, the if, as long as that one stays the same, I believe the shortest path will still be found. Now, I don't have actually a proof. This is just me working, sort of working this out in my head. Given the past 20 seconds or so, so I cannot answer that question for sure. But I believe how you choose a vertex out of Q does not break the algorithm. In other words, if you just choose the worst possible choice from Q, the algorithm should still be able to find the shortest path. All right, and then Jonathan W said, I've kind of wondered what if a path isn't possible from a point to another point. If a vertex is cannot reach a destination, then the L value of that vertex would remain infinity. That is correct, because there's no way for the expansion. Remember the cockroaches that we nailed into each cell in a maze? So you basically have a completely concealed cell that has a cockroach in it. That cockroach will not die from the pesticide. Period. Okay, and that's why that's kind of a graphical way and graphic way to kind of imagine what happens when you have a vertex that is not connected to a destination in any way. Is that working, Jonathan? Is that cockroach picture happening in your head? I grew up with cockroaches, the ones that are really big and they can fly, and they're kind of like an armored truck. You can hit them, and they just keep running. They just keep crawling away. And sometimes the small ones would get stuck in a toothbrush of all places. Yeah. Yep. Exactly. Yep. You're most welcome. You're most welcome. Okay, that's kind of funny. hmm Well, at least they have eaten good stuff, so they are probably not toxic to ingest. Anyway, all right. So let's go back to the to the homework because there was a request to go over the homework. So let's go ahead and do that. All right. So this is your homework. We are given a particular set of V, a particular set of E, D, the distance, and we want to use Dijkstra's algorithm and use this kind of representation using the spreadsheet. So we're gonna take a quick look. All right, so this is how I want it to look like. And obviously, in this case, you don't have A, B, C, D, E. We only got A, B, C, D in this case. All right, so I'm trying to figure out, how to set this up. I didn't quite imagine that, I would want to go over this, but that's okay. I can. Oh, I know what to do. Let's peel this off. Okay, I can just drag it out. There we go. And then what we can do is to overlay this with the homework description. Because I was really kind of planning to talk about, what was I about to talk about? I was about to talk about recursion today, so I was kind of, I got all the preps for that, but not so much for reviewing the homework. That's okay, we can certainly do this. I'll kind of do it the long way. So the long way to do this is to take a screenshot of this and then put it into a viewer like this, and then have it to be on top all the time, always on top. There we go. And now we can kind of show the spreadsheet at the same time. There we go. All right, so I'm going to duplicate the sheet. Okay, this part is out of the screen, but I don't think it's really important because all I'm doing is to duplicate the sheet. So this way we can sort of start from scratch, but not exactly from scratch. All right, so let me get rid of all this stuff, and we don't have L of E to worry about, so get rid of that column. All right. Okay, so let's take a closer look. Let's see. D is the destination, so that D is the only destination in this case. So I'm going to highlight D and make this one not highlight. Okay, unboldface this, and then boldface this. There we go. Alright, so this is what we have, and what we're going to do is to do some initialization. So for the initialization, E prime is initialized to be an empty set. V and W do not have any significance until we actually get into the algorithm. And then all the L values are infinity except for the one for our destination, which is vertex D. So this one has a value of 0. And then Q is initialized with all the destination vertices, and the only one that we have is vertex D. So this is the kind of the start condition of the whole thing. And what I can now do is to overlay so that this way I can show the algorithm and also be able to see the question or see the graph at the same time. All right, so this is kind of interesting, because this is probably the first time that we only use a text description of the graph instead of a graphical representation of a graph, but it should still work the same way, right? All right, so the first part of the algorithm is to select a cell or select a vertex out of the set Q, the one that has the least L value. That's pretty easy because we only got one element in Q, so that has to be the one that we're going to choose. So V is going to get the value of D, and then the set Q is going to be empty. And now we have to look at all the incoming edges to D. In other words, what edges go to D, and we got two edges going to D. One is BD and one is CD. Now the order of evaluating these two edges really doesn't matter, okay? Because either way, you are just going to update, potentially update the L value of one of them. And because these are two different edges, you cannot be updating you cannot be updating the same vertex twice, okay? And as a result, the order really does not matter. So we're going to go for BD first, okay? So there we go. And now we want to calculate, what is the potential new L value from vertex B. So that depends on the distance function. So this D is not vertex D, this is the distance function. So from D to D is an edge of a cost of 3, and 3 is less than infinity. So we have to update the L value of B to become 3. And then the edge is going to be in E prime. So that's why we have to put BD as an edge in E prime. And then we also have to add I think I want to do a slight change here. So I'm gonna put these items onto the next row. So this way the selection of the vertex is separated from the action of the conditional statement. So we're gonna have to make some changes. Oh, this is not nice. It pasted things to the wrong places, unfortunately. Okay, so B goes here, and then 3 goes here, and then get rid of these two items, like that. Okay. It should not matter, Jonathan. Choosing B instead of C, really should not matter. Okay, so we also have one more thing to do, because now that B has a new L value, we have to put it into the set Q. So that would put B into here. So the Q set is no longer empty at this point. The next edge we're going to look at is the one that's coming from C, because CD is an edge, that ends up at vertex D. So now we look at the edge CD, and then we ask the question: is vertex C getting a path that is shorter than the one that it has right now? Well, the one that it has right now has a length of infinity, so we are pretty sure that we have just found a shorter path. The question is, how short is that path? Well, it's a single edge to a destination, so the distance of the edge is 1. So the new L value of C is going to be a 1 in this case. Now, because we are updating the L value of C, we also have to change change a few things. So E prime now also would have the edge CD in it, and then vertex C will also be added to the set Q, because vertex C just got its L value updated. So that would conclude the for each loop, because we have considered all. Oh wait, that's AD too. So I'm not quite done yet. So vertex A is another vertex that has a single edge to get to vertex D, so we have to also consider that. Now, since L of A is infinity at this point, so that means we are pretty sure that we just found a shorter path. So that the length of that shorter path is just the edge of AD, which is 11. So we update the L value of A to be 11. And then we have to add that as an edge into E prime. So E prime would now also contain the edge, AD, and the vertex A would also be added to the set Q. Okay, so Control B, and there we go. All right, so let me just double check. Pretty sure I got everything, unless D is a loop back to itself. So we have AD, BD, and then CD. So this time we have covered all the edges that will end up at vertex D. So that would conclude the for each loop, and then we go all the way back out to the while loop. And the while loop asks, do we still have any vertices in Q? And we got 3 this time. So we're not quite done with the while loop. So now we have to select one of the vertices from Q to become the next value of variable V. And the way we're going to choose is to choose the one that has the least L value. And I just mentioned earlier, if you did not do that, I believe the algorithm will still complete correctly. You're finding the all the shortest paths from all the vertices to one of the destination vertices. The reason why I said that is because sometimes people do not use a set representation for the set queue. Okay, sometimes people are just kind of lazy, and they just use a stack to do it. Okay, so they just push something onto a stack. So queue is not implemented as a set, but it is actually implemented as a stack. And when you're talking about a stack, the order is last in first out, and I believe those algorithms would also guarantee to find the shortest path. But I'm going to follow my algorithm because I want to show you what the correct answer looks like. Alright, so out of A, B, and C, we're going to choose the one that has the least L value, and that one, the winner is going to be vertex C. And now we have to look into all the incoming edges to vertex C. But before we do that, we have to remember that vertex C is no longer in the set queue. So whatever vertex you choose out of the queue set, in order to explore all the incoming edges into that particular vertex, you have to remove it from the set queue. Alright, so now we're going to look into this and find out who ends up at vertex C. Looks like only B is a vertex that ends up at vertex C, so BC is going to be the edge that we are looking into. So now the question is, what is the length of this alternative path from vertex B to the destination? Well, it's going to be whatever the distance is from B to C, which is 2, plus whatever the L value of B currently is. And that would be the L value of B of C, not B, sorry. So that is a value of 1. So we are looking at 2 plus 1, which is a 3. So this is where at least one of you asked me about, okay, so we have an equal in this case, right? Because L of B is a 3. L of C plus the distance from B to C, which is 2, 2 plus 1 is also 3. What are we going to do? Well, you just have to follow the algorithm. Okay, I believe the algorithm says we only want to do something when we find a shorter path. Okay, this is just as short, and as a result, we do not update anything. So we just go like, yeah, but we didn't quite find a new path, so we do not perform anything. Okay, so we are now going back, and that ends the for each loop too. Exactly, so Armand is correct in the text, because it is not less than, we did not find a shorter path, and as a result we just goes like, the one that we found earlier was just as good as this one. There's no need to go through updates unnecessarily. Yep. Alright, so now what do? We are done with the for each loop, and now we're going back to the while loop. The while loop says, yep. The while loop says if Q is not empty, we still got work to do. Yeah. Well, they're just as good. Okay, the previous path is as good as the new one, so there's no need to make updates unnecessarily. Alright, so now we are back to the while loop. The while loop says we cannot exit yet because we still have B and A in the set queue. Now we have to choose between those two. So between those two, which one has the least L value? So we are talking about A and B in this case. A has an L value of 11, and then B has an L value of 3, so we're going to choose B. And as a result, B is removed from the set queue, and now we look into all the incoming edges to B. Let's see, there are only one edge. There's only one edge, and that's going to end up at vertex B, and that is from A to B. So now we look at the new path. Okay, we're now looking at the length of the new path from A to B, and then from B to the destination. That's going to be a path, not necessarily a single edge. So the length of that path is going to be whatever the L value of B is, which is 3, plus the distance between A and B as a single edge, which is 1. So we are now looking at 1 plus 3, which is a 4, and we are asking 4 being the length of the new path that we have just found. Is that shorter than the current path, the length of the current path from A to a destination, which is 11? The answer is yep. That is the case. So now we're going to update L, the L of A to become 4. We are also going to go to the E prime set, and we remove the existing edge from AD, that's coming from vertex A to another vertex, and then we're going to replace it with the edge of AB. So if I combine both operations into one, which is okay if you did that also in your answer, and we have AB as an edge instead of AD as an edge. Now we also have to add vertex A into the set, but it's already in the set, so the set Q is almost as if we didn't do a single thing to it. Alright, so that would end the for each loop. And after the for each loop, we go back to the while loop, and the while loop says, is Q empty? Nope, Q is not empty. We still have one vertex in it. Since it only has one single vertex, it has to be the one that we're going to choose out of the set Q. So now V is A, and then at the same time we remove vertex A from the set Q, and now we want to look at all the incoming edges to A. And in this case, we don't have a single incoming edge to vertex A, so that loop is the for each loop has nothing to do. There's zero iteration for the for each loop, and then we're now back to the while loop. The while loop looks at the set Q. It is indeed empty, so now we can finally exit the while loop, and the algorithm is done. So this is the answer to it's the solution. This is the solution, okay? And some people ask me, there's an extra edge in this particular set here, because it looks like we can go from A to B and then B to D, so that edge CD seems to be extra. Should we remove it? The answer is exactly. So Aman is correct. The edge CD is necessary because remember, this modified Dijkstra's algorithm finds the shortest path from every vertex to a destination. So the edge CD is also the path from vertex C to a destination. So it cannot be removed. It needs to be here because we are not looking for a single shortest path from a vertex to the destination. We are looking for the shortest path from every single vertex to a destination. So I hope this kind of answers the question. Are there any points you guys want to make? Any questions about the trace before we move on to talk about recursion? Alright, so Aman is typing. And I do understand how this can be a little confusing for people who are taking CISP440 in the same semester, because Iraj's algorithm is kind of the opposite of this. I think it starts with the start vertex and it works its way to the destination. Alright, so one thing I'm having trouble with is summarizing the entire algorithm. I don't have the intuition to explain it without working through the algorithm. Well, that's sort of why I explain what each part is trying to do in the algorithm. But in the end, it is abstract. I mean, that there's no pretense. Okay, there's no way to say that this is not abstract. This is one of those algorithms that is, you just kind of have to let it sink in. That's kind of the only way for me to describe the process, to kind of make sense of the algorithm, is really just to kind of work through a few different examples and then try to figure out what each line, what each statement is accomplishing in the entire thing. Why is this necessary? What happens if this is not here? So we are, asking those questions can really help you understand the algorithm and understand why each part is essential to the algorithm itself. And then wait typed just had some confusion formatting the trace. That's okay. I mean, if your trace is not formatted exactly the same as what I have here, but the sequence of the updates are correct, it will still be fine. Not a problem. Okay, so I'm not gonna nitpick on notations. All right. Any other questions? I think our class has gotten much smaller now. All right, so we got 2 people typing, and I'm got 3 people typing. All right, excellent. All right, cockroaches. Well, at least cockroaches are not poisonous. Wait until you hear all the horror stories from Australians. All right, Q can be selected to be whatever initially. No, the initial value of Q is the set of all the destination vertices. That's how it should be initialized. Yep, exactly. Is it Pai Chi? My Mandarin pronunciation is really, really bad. I heard. Yeah, that was my cat. Oh. Yes, absolutely. YouTube is rewindable, and that's why I record everything onto YouTube, because this way you guys can kind of watch the important part, again. And that's also why you might want to keep a timestamp of all of those kind of tricky points, so that way you can just kind of fast forward to the point where you need to watch it again. Oh, okay, yeah. So, I'm not gonna do it this time, but I can work out an example, so that way next time we can give it a try. Okay, and an example where there are multiple destinations, and we can even have vertices that cannot even reach a particular destination. So in other words, it's completely isolated by itself. So that way it will be kind of obvious, to see how the L value of a vertex that cannot get to a destination would remain infinity, like forever. Yep. Okay. So remind me to do that maybe at the end of today's class, because I really, really want to talk about recursion. Alrighty. Okay, so let's go ahead and talk about recursion. I'm going to take this out here. And you have the solution, because everybody can actually still see the same spreadsheet. So you got the solution if you want to refer to it. And I'm going to close this window because I don't need that anymore. Oh, that's right. We were talking about predicate calculus. So we are not quite done with it, because I still haven't talked about the mechanism of Prolog. So let's go ahead and do that part. Yeah, I'm pretty sure you guys can hear that too. Yep. Yep. All right. So let's move on and talk about the mechanism of Prolog. That is a very good question, Aman. I do not know yet what to do with it. The plan is I want to give you at least one homework assignment, so that you can actually practice using Prolog. I don't want to turn the exam into programming work, so not really quite sure how to work the Prolog thing into it. So Um, I'm not sorry. Sorry, I apologize. I cannot really answer that question. Not that I don't want to. I simply do not have the answer at this point. All right. So, okay, so we already kind of know what Prolog does. Okay, you can state a bunch of facts, which are basically just a rule that has only specific atoms to specific predicates. So the question is, what is the mechanism behind Prolog? So the main mechanism behind Prolog is the concept of substitution. So what we can do is we are using this as an example. Okay, so phi in this case is a particular rule in Prolog. Okay, so this is the one where it reads as is a proper Jedi X only if is a Jedi X and owns XY and is a lightsaber Y. Okay, so we talked about this last Wednesday. Except, of course, when you look at this as an implication, everything is kind of backwards. Okay, the right hand side and the right hand side and the left hand side, they're switched. Okay, but this is the actual implication. Okay, this is the implication. It's kind of like what you have in iota when we talked about propositional logic. Okay, this implication is just given to be true. Okay, don't ask me why. Okay, this is a weird Star Wars universe, and this is a known fact. Okay, that's just given to you, just as these facts are. Okay, so Anakin Blue is a lightsaber. Don't ask me why that is a fact, but it is a fact. The fact that Luke Skywalker owns Anakin Blue is also just a fact. Okay, so this particular rule is also quote unquote a fact. It is a given truth in that particular universe, and I'm using phi in this case to represent this particular rule, which is basically an implication that has variables. Now the entire thing is more like this, okay? Because we have x being universally quantified, y being existentially quantified, but we are not gonna put that here. So the mechanism used by Prolog is substitution. So in this case, we are basically asking the question, what can make this whole thing true? So what value can go into x, what value can go into y, still be consistent with all the facts that we have already established, and at the same time make this particular rule, make this implication true. So that is what we are asking, and the mechanism, the underlying mechanism, is called substitution. So substitution looks like this. Okay, it is in fact a set. Okay, so for those of you who looked at these curly braces and go like, "Tech, is that a set?" The answer is yes, it is a set, where each element is a kind of is a mapping. Okay, you can call it a mapping. Basically, it is mapping the unbound variable x to the atom of Luke Skywalker, and then y is mapped to Anakin Blue. And then the application of the substitution, as you probably guessed it, okay, every time we see an X, we replace it with Luke Skywalker. Every time we see a Y, we replace it with Anakin Blue. So as a result, okay, this is the notation of applying substitution S to the implication of phi. So the end result of that is this spelled out implication. And in this case, this spelled out implication is in fact true. Now, how do we know it is true? Okay, because it's just a blind substitution. You could have used other things to do the substitution. The question is, after the substitution, do we have this implication being true? And in this case, it is true because is a Jedi Luke Skywalker is true by itself. Okay, it is a fact that was established earlier as a fact, and owns Luke Skywalker Anakin Blue is also a fact. Is a lightsaber Anakin Blue is also a fact. So these things individually is true. So we have true and true and true. And now we have the implication. So if the rule itself is true and you have the antecedent being true, then the consequent has to be true. So this is why we can make a conclusion that is a proper Jedi Luke Skywalker also has to be true, even though this one is not given to us explicitly as a fact. The rule can now be used to prove that it is true. So there we go. And that's basically what we have here, because we know the individual facts are known to be true. So we have true implies is a proper Jedi, and that means it's a proper Jedi. Is a proper Jedi Luke Skywalker has to be true because the implication itself is known to be true. Because phi is known to be true, yes. So basically this phi here is kind of like something that we would put into iota when we talked about propositional logic. In other words, your entire program, okay, in Prolog, all of those things in Prolog is basically items in quote-unquote iota, okay, except in propositional logic, for some reason they don't call this the set of iota, but it is equivalent to what we know as the set of iota when we talked about propositional logic. So are we doing okay so far with this? It's more like phi is an element of iota. So this is basically an element of iota because it is a quantified statement that is known to be true. Yes, so phi is an element in iota. That is correct. Except we don't use the term iota when we talk about predicate calculus. All right, so we talked about disjunction already. It is the semicolon, and we also talked about negation, which is something that cannot be proven. Okay, so if something cannot be proven, it is negate. We say the negation is true. So that's it. Alrighty. Any questions about Prolog or propositional logic? So the only thing I added today was the mechanism of substitution. Okay. I will make an assignment for this and give it to you guys on Wednesday. Okay, cool. All right. So with that, the one thing you can also do is really kind of to replicate what we have here. This is basically the fragments of one single program written in pieces. You can also enter the program that I have used last Wednesday, which is about ancestry. So you can include those things. And one thing you can do, okay, I might actually turn this into an assignment, is how do you describe cousins? So assuming that we have parenthood representation, okay, so who is whose parent, okay, so let's say we have that representation. We have gender representation, okay, which is not entirely necessary, okay, unless you are in a culture where the cousins from mom's side have a different term compared to cousins from dad's side. Yes, Chinese culture is one of those. So unless you're in a culture like that, cousins are cousins, right? But we also want to kind of talk about cousins. How is that term? Fourth cousin, two removed or something like that, meaning that they are actually of different generations, right? So how do we express that? Okay, so think about that a little bit. Okay, so on Wednesday I'll give you the official homework assignment, but right now you can kind of think about it, is to say, okay, if I know who is whose parent, I have ancestry already defined the way that I talked about already, but we want to be able to find cousins that are using that term, okay, the phrase of fourth cousin, third cousin, but you can also have a number removed, which means now they're not in the same generation. Okay, think about parenting or parenthood as a tree. Okay, so normally when we think about cousins, the cousins are at the same level of the tree. So when you have related people but they're at different levels of a tree, they are still called cousins, but they are like X number removed. So let me try to find that definition. Cousins removed. Okay, there we go. Okay, cousin chart, family relationship explained. There we go. complicated stuff, much more so than lottery. So here's a good example. Let me put the link in Discord so you can take a look at that. All right, so the idea is I want to be able to specify not only cousins, but I also want to be able to specify second cousin, third cousin, and so on. Make it a parameter, and also want to be able to specify x removed from being cousins, which means now they are not at the same level of the tree. One is closer to the root and the other one is actually further from the root, but they're still called cousins. So I think there we go. Once removed, then you have twice removed, and so on. Because that's really just saying they are not at the same distance from the root in terms of how many vertices are in between. See how this stuff they're all kind of related, right? Because we can look at ancestry as a graph, okay? And it's a strange kind of graph because it's a tree. Yep, exactly. So what is a tree? How is a tree different from a general graph? What can you say about a tree that is different from a general graph? Certain things are guaranteed. Well, it goes down or goes up, depending on the direction of the vertex of the edges. Okay, cannot loop. Okay, that's one. That's very good. Okay, cannot loop, and there's one more. From a root, there's only one path to the other vertices. You cannot find two paths to a vertex from the root. In fact, you can only find one path, between vertices. You cannot have two paths from one vertex to another vertex. Now, there are some vertices where they do not have a path. That's perfectly okay. Like the leaves, cannot go to each other. But if you look at vertices that are connected by edges, there's only one path, okay, to go from one vertex to another vertex. So that makes it kind of special because without the loops, without multiple paths to the same vertex, it does make a whole lot of things easier to deal with. So anyway, this is an interesting article that explains how we call relatives cousins. So the idea is we want to code this into Prolog so that we can express cousins, first cousin, second cousin, third cousin, and then we also want to be able to specify how many times removed. So we want to be able to specify like fourth cousin twice removed, something like that. Yeah, so that's gonna be what we are going to do for the next homework assignment that I'll assign on Wednesday. But you can start to think about it, okay? Because you can just kind of try to code all of this in predicates. Okay, so I'm gonna just kind of leave that to you. There are a few tricks that you probably want to know about. Is you can actually use calculations. And there's a way to check for equality in Prolog because you will need all of those things. So I'm gonna show you how to do that. I'm just searching for SWI Prolog compare. And all right, so there we go. So we have examples to. You can also use switch to kind of play around with all this stuff here. All right, so you might want to find some, get some time to kind of read comparison in Prolog. There we go. Very surprising here. We have equal to, not equal to, less than, greater than, less than or equal to, and greater than or equal to. And then you can also perform calculations like addition, subtraction, multiplication, and division. Usual regular syntax. Okay, so that's can be helpful, hopefully. All right, so Aman is typing something. Oh, sure, absolutely. There we go. All right, cool. So now we are going back and start to talk about recursion. I'm looking at the time. We got a good amount of time to talk about recursion. Alrighty, so we are going back. Okay, so we're back. We're going back in time to big O, ohm, and theta, and we are going to recursive definitions and algorithms. So we're going to go to this slide here and open it up. I believe I already have it opened up, but that's fine. All right. So the first idea is, what exactly is recursion? So recursive definition is one that refers to itself. And in this case, I can define factorial recursively. So if I want to define factorial recursively, then the way I do it is going to be for all n that is in positive integers. So z plus is positive integers. So n is greater than or equal to 1 implies n factorial is n times the factorial of n minus 1. And then I define 0 factorial to be 1. So this is a recursive definition. And using this particular definition, the way we figure out what the value of 4 factorial is going to be, we look at 4 factorial, and then we look at these two rules, and we ask, are we looking at 0 factorial? No. Then we have to be using the other rule, which is 4 factorial is 4 times 3 factorial. So we know what 4 is, not a problem. We know what multiplication is, not a problem. But what is 3 factorial? So now we applied the same logic. Okay, so we check for the base case first, and we ask, are we trying to figure out 0 factorial? No. Okay, so we now have to look at the recursive definition again. 3 factorial is 3 times 2 factorial, and then 2 factorial is 2 times 1 factorial. 1 factorial is 1 times 0 factorial. Woohoo! Finally, we got to 0 factorial, because that's the one that we know what the answer is like by definition. So 0 factorial is 1. That's by definition. So we now substitute 0 factorial with a value of 1, and then we end up with, oh, so we are just trying to multiply 2 with 1 and then 1, and that becomes 2. And then we have 3 times 2, which is 6, and then we have 4 times 6, which is 24. So are we okay with this example? You know, how factorial itself can be defined recursively. Yes, you can use 1 factorial being a 1, but then if someone asks you what is 0 factorial, then you would not have an answer for that. Okay. Yeah, so you really should use 0 factorial is 1 being the base case, because there's meaning in 0 factorial. Because remember when we talked about combinations and permutations, occasionally we run into the situation where we have to figure out what is 0 factorial, and it makes sense that 0 factorial is 1. So that's why, even though in most cases we can end with defining 1 factorial as 1, it is better to use 0 factorial being 1 as the base case. So this is a recursive definition, and other recursive definitions would include GNU. Okay, so for those of you who know what GCC is representing, GCC represents GNU C compiler. Okay, and so the question is, what is GNU? GNU is by definition, GNU is not Unix. In other words, when you expand GNU as an abbreviation into its definition, you get into the term again. And then when you expand that again, it becomes GNU is not Unix again. So it's kind of like the story, of oh, okay, that's a Chinese thing. I'm not going to mention it. Basically, the storyline goes like, there's a monk living on a mountain. Oh, there's a temple on a mountain, and the monk lives in that mountain. And the monk is telling a story. What is the story about? It is about a temple on a mountain, and in the temple is a monk, and that monk is telling a story. What story is that monk telling? And you just keep going and going and going. It is recursion. So, do we have any questions about recursion itself? What is a recursive definition? Okay. Yep, and you can just you record yourself once and then put it on a repeat loop and just let it keep going and going. It's an endless recursion, except we don't have a stack to overflow in this case. I suppose you can call the energy level of the child as the stack. So when that runs out, you have a child falling asleep. Yep, there you go. Okay, so now we are looking at actual implementations using recursive definitions. So one is just resembling what we talked about earlier. This is not the best representation, but it will suffice. Okay, this is factorial implemented in a recursive way, and this is actual C code. So f of n is, if n is greater than 0, then the result is n times the factorial of n minus 1. Otherwise, now I know this is poor logic here because I use the type int here, which means n can be negative, and negative integer factorial doesn't make sense. Okay, but in this case, I'm just saying if it is not greater than 0, we'll just call the factorial of that integer being a 1. And the reason why you do not see a return here or a return here is I really do not like having returns sprinkled within a subroutine. So that's why I have a local variable called res, which stands for result. And for each branch, I remember what the result is supposed to be, and I have one single return statement at the very end of the function definition. So, styles not taking into consideration, are we kind of relating this implementation in C to the recursive definition of factorial up here? Is that okay? Are there any questions linking the mathematical recursive definition of recursion with the actual C implementation of the same thing? So no questions about that? Okay. And I would even suggest you guys to kind of do this a few times. Okay, just write this code, and inside main, go ahead and call f. Try to find out what is f of some smaller number like 4 or 5. Okay, and you also want to put a breakpoint. Okay, so I would put a breakpoint right here on line 10, or what is line 10 in this code here, because at some point this algorithm will stop. When it does stop, okay, you want to use BT, which is backtrace, to find out how the different levels of calling the subroutine again and again and again. Okay, so one thing that a lot of people have they ask about recursive definitions, and at least in the case of implementation in C and C++, is what about this local variable res here, and what about this parameter n over here? So when f is calling itself, what's going to happen to the local variable res, and what is going to happen to the parameter n? So the answer to that question is kind of tricky, because it's difficult to explain that without understanding how things are organized in memory on the stack in assembly language. Yes, Jonathan is in my CISP440, so we are just at this point too. So we are really just talking about how local variables and parameters are living on the stack. So they're actually each invocation of a subroutine has its own copy, has its own own set of local variables as well as parameters. So there's no way the same thing can be overwritten unnecessarily. The only way for you to overwrite the same thing over and over again is to declare a local variable static. And that would be it's very, very few occasions where it does come in handy, but it's very, very seldom. So are we good with the recursive implementation of factorial? Okay, good. This is actually a very lengthy way to specify recursion to specify factorial as a recursive definition. I'll give you the really short one, and I'll have you guys kind of think about it if you want to. Yeah, using unsigned would be the better way to go. But I can give you a almost one-line version of this. Okay, so we're going to use Jonathan W's suggestion and use an unsigned type, so this way we don't have to deal with negative values. So f unsigned n, which is our only parameter. Okay, and the whole thing has one single return statement because I can use, guess what, ternary expressions. So now we can say if n does equal to 0, we want to return a value of 1. Otherwise, we return n times f of n minus 1. And there we go. Same code, same logic. Well, I mean, I changed the types. But other than that, it really is the same logic. Except this one is super condensed into one line because I am using a ternary expression instead of if then else to specify the same logic. Ternary expressions are extremely useful. They're difficult to read only because people are not using it enough. If it is used enough, it is actually, yes. I feel like your classes make them easier for me to read now. Not sure whether that's a compliment or not. Okay, so just to make things a little bit more cryptic, that will also work. Because n is an integer, right? So in a context where a boolean is expected, the way we interpret an integer is 0 is false, anything other than 0 is true. So if n is indeed a 0, it is interpreted as false, as the value being negated upon. So the negated false is true. So in that case, when n is 0, then we'll return a value of 1. For all other cases, we're going to return n times f of n minus 1. So this makes it even more cryptic, but a little bit shorter. Now, if you want to make it like super short, we can get rid of the not here, and then just flip these two. This makes it even shorter. There we go. Yep. Doesn't make it very easy to read, but it is one way to represent exactly the same logic. So there we go. Yep, you can do that. Certainly, you can do that. All right, so what else can be turned recursive and remove spaces? I believe you still need a space between. Oh, you don't need it. You don't need that space because we have a open paren here, so that space is actually not needed. So we can basically compress all the spaces. Yep, there we go. So the whole thing can go without spaces, except between these two. I think that space is still needed. Oh yeah, absolutely. This is called obfuscation. There are programs designed specifically to obfuscate, source code, and also the code compiled from source code, so that it's difficult to decompile the assembly code back into the nice structured code of the same logic. Yep, sort of. Alrighty, so let's talk about something else. Okay, let's talk about string. Okay, we can do string compare, we can do string copy, we can do string and copy, and so on. Let's just do string copy. Okay, there we go. All right, so string copy. Okay, if you look up online, what it does. Okay, so string copy. By the way, you really should not be using string copy because it is unsafe. Okay, it doesn't have it's not length terminating, so that means it is susceptible to Stack Overflow exploits. So do not use string copy. but I'm using it as an example. Okay, so I'm just using it as an example here. All right, so it copies a string. The first parameter is the destination. The second parameter is the where we're copying from, and then it returns the destination itself, so the whole thing can chain with other string functions. Okay, so the question is, how are we going to implement this? If you want to keep your code short, you have to do sunglasses. What you have to do? All right, so we kind of know what string copy does, okay, even though it's not exactly a good idea to use string copy, because you really should be using string and copy when you're copying a string. So this way, at least you can specify only up to this many characters, but do not exceed that. Okay, but I'm going to use it just as an example. So the usual way people do this, okay, so I'm going to implement string copy here. So we start with a destination, and then we have const char star source. There we go. All right, so the typical way to do this is rather boring, which is basically just going like, oh, okay, all we need to do is to increment both until we get to a null. After we copy the null character, then we are done. Okay, but we also have to remember to return the original destination. So you got a few ways to do this. You can have a local variable called pointer, which is initialized to dest destination, and then you can say while. Let's see how cryptic we can make this. Okay, so while star ptr equals to star src, and then we'll use post increment in both cases, and then we'll just put a close parent here, and then put a semicolon here, and then we say return dest. Okay, let me double check. See if this makes sense. Yeah, that makes sense to me. Makes perfect sense to me. It's all good. All right. So, do we have any questions about this code? This is not recursive. This is the non-recursive. This is the easy way to implement string copy. Okay, I'll give you guys a moment, because I'm pretty sure you have to take CISP440 before 400 and then 400 before 430. So the comparison is done. Well, there's no comparison. This is assignment, actually. This is a single equal. It is an assignment operator, where some compilers would actually give you a warning and say, are you really sure that you want to do a comparison in a context where a condition is expected? And the answer is yes, I really intend this to be an assignment. Well, you can keep assigning continue. Okay, so when does the loop stop? Very good question there. Well, the loop stops when the expression is giving you a value of 0. So when this expression gives you a value of 0, it stops, right? Because the false condition will get you out of a while loop. So the question is, but we are not even comparing. How do we get a false, right? So as it turns out, the assignment operator will give you, it has its own value, okay? Most people think about assignment as a statement, okay? Meaning that, oh, you can only have one assignment, and then you have to end it with a semicolon. That is actually not the case. In C, assignment is an operator, which means it forms an expression, and that expression has its own value. So the value of an assignment expression is the right-hand side of the assignment. In other words, this is the value of the entire assignment expression, because it is the right-hand side of the assignment. And what is that? Well, is it giving you a pointer? Is it giving you what the pointer is pointing to? And if it is giving you whatever the pointer is pointing to, is it giving you what it's pointing to before or after the increment? So all of those are questions that you need to kind of think about, okay? So we'll answer those questions one by one, step by step. Okay, so let's start with this operation over here. the first thing we see is SCR++, and then we see SCR++, and then we see the asterisk. So if you do not remember the operator precedence of operators in C and C++, that's okay. I can use extra parentheses to tell you exactly how they're ordered. So source++ is the first thing that happens. But because it's a post increment, so that means the value of src++ is the pointer before it is incremented. Okay? And then that gets dereferenced. In other words, this entire thing is going to be the value of the byte that source is pointing to before the increment. What are we going to do with this, right? This is an assignment operator, which means we're copying whatever the right-hand side is to the left-hand side. So the left-hand side is the same thing. Okay, the operator precedence is exactly the same as the one on the right-hand side. So this means what we are copying this value to, whatever source is pointing to before the increment, is whatever location PTR is pointing to before its own increment. In other words, I'm just copying whatever source is pointing to whatever PTR is pointing to, and then we increment both of them at the same time after the assignment is performed. Are we doing okay so far with this? Are you guys kind of following? All right. Any questions? That might get a little bit difficult, but I can outline the the actual operations, but I'll get to that in just a moment, okay? But the question is, this entire thing is supposed to be an assignment expression which has its own value. But we already know its own value is just whatever source is pointing to. So that means I am looking at whatever source is pointing to and say, okay, look at that and evaluate it as a Boolean. Then you go like, but it's a char, it's not a Boolean. Well, there's no actual type of bool, B-O-O-L, in C. That's a C++ kind of thing, not a C kind of thing. So the way we look at this is, okay, this is a Boolean context. We want something that is either true or false, but I'm only given with a char. So the way we do it is, okay, it's just like an integer. Okay, if it is a 0, which means it's a null character, it is interpreted as false, and that will get us out of the loop. If it is anything other than 0, if it is non-null, it is interpreted as true, which means we're going to go for the next iteration. So let me go back to Aman's question. Okay, so I'm going to use comment here to kind of indicate what is actually happening. So what is actually happening is kind of like this, okay? It's kind of like PTR, star PTR gets star SRC, which you probably already know. Yeah, we kind of know that is what we need to do. And then followed by the increment of both, okay? So increment, so SRC plus equal to 1, PTR plus equal to 1. That is kind of the sequence of what we are doing here, except whatever SRC is pointing to is also being used as the value of the entire assignment operator here. So that means we are sort of doing this, okay? We're sort of doing a TMP equals to, and the reason why an assignment expression it returns the value of the right hand side is that we can chain something like this. Okay, so then at the very end here, we are using the value of TMP as the value that we are interpreting in the context of a condition. So if TMP is 0, which means we just copied the null character, then we get out of the loop. If TMP is non-zero, which means we copied something from the source to the destination, but it is non-null, that means, okay, keep going, because we are supposed to copy including the null terminator before we can stop the loop. They mean the same thing, Jonathan, because 0 is one of those really strange things where it is typeless. So 0 can be interpreted as signed integer 0, unsigned integer 0, a void pointer 0, which is also called null. It can also automatically cast to the null character itself. Yeah, so yeah, so you have been told to use something like this to mean the null character, but this really is the same thing as this, which is the same thing as this. Which also, by the way, is the same thing as this, or this, or this, and so on. Because they are all just zeros. Every single one of these is specifying 0. It just has many faces, that's all. Alright, so are we doing okay so far with this really cryptic, non-recursive version of string compare? Just when you think, yeah, I took CISP360 and then I took CISP400 and then I'm taking CISP430. Of course I know C, well, sometimes, you just kind of, you have to, you have to expose yourself to all kinds of programming in a particular language to really understand all the different things you can do with a programming language. I'm not encouraging you guys to try to make your code as cryptic as possible. That's not the message here. The message here is you should be able to understand it. If you claim that, yes, I know how loops work, I know how while works, I know how post increment works, I know how dereference works, I know how assignment works, then you should be able to interpret this. But the question is, do you actually know that assignment is an expression and not a statement in C? In other words, you can embed something equals to something, an assignment, inside a place where you can expect just a numerical value. Any place. So that's one thing. That's the one thing that most people do not know, is you can actually do it like that. Now, I know it sounds like, oh, tech is, you're just telling us, you're just showing us really cryptic code here. Well, that may be the case. However, sometimes you intend to use two equals because you want to compare, and then you have a typo. You have only one single equal. In some cases, it is not okay in the context, and then your compiler will complain about it and go like, hey, you cannot use an assignment here because the left-hand side, guess what, is not something that you can change. So in that case, if you say 2 equals x, okay, then it's not going to work because you cannot assign a value of something to a constant, to a literal constant of 2. That is not okay. And then the compiler will stop right there and say, nope, cannot do this. On the other hand, if in this context here, if you really intend to just compare, but you mistype the comparison, the equality to a single equal, unless you turn on the warnings of a compiler, the compiler would just say, hey, guess what? Syntactically, this is perfectly okay. I'm not really quite sure why you want to do an assignment as a part of a condition, but guess what? Syntactically, it is okay. You pass, not a problem. It is only when you run the code that is not going to do what you think it is supposed to do, then it is a difficult bug to fix. It's a difficult bug to fix because in the context of this, it will return a value that can be interpreted as either Boolean. It's either one or true or false. So it would actually do something, right? But in doing that, it will also change whatever the left-hand side is specifying. In other words, it has a side effect that you are not aware of. So it's changing something, okay, while you do not expect it to be changing something. And then later on, when you need to refer to that something that had been changed by this loop here, you would not go back and expect it is this loop that did all the changes and you didn't anticipate it. So that means by the time the symptom shows up, okay, when you need to refer to whatever that I have highlighted here later on in the algorithm, that it has changed and you have no idea why or how it got changed. So that's one of the most difficult kind of bug to fix, is the effect happened way earlier, and then by the time you see the symptoms, it is much later. So it's much harder to actually associate the code that happened way earlier to the symptom that happened way later. All right, so I'm going to turn this into a recursive version. Okay, I'm turning into a recursive algorithm now. So you look at this and go like, oh, attack, I don't see really how this can be done recursively. Nobody has said anything about doing a recursive string copy. Well, let's do this step by step and see how we can do this. Okay, so I'm going to have the same thing over here. Yeah, we have a few minutes left, but I think that's probably enough time to do it. Alright, so when you think about implementing something recursively, the first thing you want to think about is the terminating case. Terminating case. There we go. In other words, when do we not need to do any recursion? Well, in this case, the case where we do not need any recursion is when source is already pointing to a null character. Then we just copy it and we are done, right? So we say if well, first of all, we do a copy first. Okay, so the copy part you can do it kind of by default because that's something that you have to do regardless. So we do this first, and then we say exactly. So if not star source, okay, or if you it's you have to use the dereference because we are not checking whether the pointer itself is null or not. We want to check if the pointer is pointing to a null character or not. So in this case, we can say got nothing to do in this case. All done. Okay. And then obviously we have to return destination because that's a part of the description of string copy. This is intentional because I think some people are just thinking, why would we want to copy something when the function is supposed to just copy a string to another string? The reason why we return destination is we can chain the return value of string copy to another string operation like string compare or whatever you want to do with that string. Okay, so this way we can chain a lot of things into one really difficult to read nested call of stuff. Okay, yes, I just said that. Okay, so now the question is, okay, what if that is not the case? What if it's not the null character that we just copied, which means we can't really stop yet? This is the case where you have to do the recursion, right? So now the question is, how do we apply this reasoning of recursion? So recursion relies on one thing, okay? It is a bigger pattern has a smaller pattern that has the very same nature as the larger pattern. So now you have to think about, but destination to string, how can a string contains a string, right? Okay, so now you have to kind of remember what a string is in C and C++. A string is no more than a pointer pointing to it's an array of characters. Okay, so that's one way to look at it. It's an array of characters. So if it's an array of characters, you take away the first character of an array. Is the rest of the array, can it be considered an array on its own? The answer is actually yes. Okay, it is also an array of its own. So now you just say, I can just say string copy, and I'm going to say we should not using dest anymore because we just got something into whatever destination is pointing to. I am going to do this. In other words, you are just adding one to each pointer, and then that becomes the new pointer, and therefore the recursive call is going like, okay, I have a smaller string to copy. It's smaller by only one char, okay, but nonetheless it is still a string, okay, and it keeps going like this until we get to the null character, until destination, until source is pointing to a null character. In that case, there's no need to do recursion anymore because this is a null string. I'm done. Just by copying that null character, I'm done. So this is a recursive way to look at string copy. What is the significance of this? The significance of this example is you can look at a lot of things that you normally would not look at as having a self-similar pattern. But if you look closely, a lot of things that we deal with in programming, arrays being one of those, actually has a self-similar pattern. And as a result, most things can be turned into a recursive type of algorithm. And not using kind of convoluted ways of doing things. This is actually not terribly convoluted. But it is a way of looking at things. Okay, so that's kind of the takeaway of today's lecture. I know I'm over time already, but this is kind of the takeaway of today's lecture is recursion is a way of looking at things. Just like object-oriented programming is a way of looking at things, the recursive way is basically looking at a self-similar kind of pattern, okay? A larger pattern that contains things, but in each component of this larger construct has a similar nature as the larger construct itself. Now remember we talked about trees earlier? A tree is a self-similar structure. Because if you think about it, if you look at a tree, now whether it's a real tree or a tree in programming, they both have a similar kind of construct or structure. Is if you take a bigger branch that has a bunch of smaller branch, you break off one of the smaller branches. Guess what? That smaller branches, even though it is smaller, has a similar construct, a similar structure, a similar characteristic as the original bigger, larger branch. So in programming, we are really looking at these things, right? A lot of things are self-similar in nature, and that's why recursion is a very useful concept. Now, practicality-wise, no, recursion is not really the best way to implement something, but from the theoretical perspective, looking at things from a recursive perspective is very useful. Okay, so I'm going to stop with just that. Okay, and then you guys can look into string compare. Okay, look at string compare, and this is going to be one of those ungraded assignment. So look at string compare and then see if you can implement that recursively. So I'll see you guys on Wednesday with an assignment for the Prolog coding stuff. Okay, so we got questions. I still have office hour right after class, so I'm gonna stay on Discord for another hour or so if you guys have any questions. In the recursive string copy, what is the benefit of returning the char pointer of dest? As I was saying earlier, it is for chaining things. Okay, so since I'm still recording and still sharing on my screen, I can show you what I mean by that. So you can now nest things, like you can do a string compare using the result of string compare, a string copy, and this is duplicate, original, and some other string. And so so you can actually do this. So you don't have to separate string compare into its own statement, because now we can combine the result of string compare with string excuse me, the other way around. You can actually combine string copy and string compare into one larger nested call of functions. Obviously, if you abuse this, you can certainly make code very, very difficult to read, and it's harder to comment because you don't have the natural end of line, per small operation to add your comment, because now everything is one single large nested call of functions. All right. Yeah, the chaining thing can be handy, because now we can say, if you can put this whole thing into a conditional statement and say if this is less than 0, which means the first thing is less than the second one, and then you can perform whatever operation you want to do here. So yeah, it does kind of enable very cryptic kind of programming, but at the same time it is very handy at times too. So yep, you too, you guys have a nice day. Yes, it does. Especially in C and C++, because in C and C++ there's no recognition of tail-end recursion, and without tail-end recursion recognition, it does chew up stack space for each call. Now, for a programming language that has detection of tail-end recursion, which I think Lisp does, it's not actually going to consume any additional stack space, because once you return from the very end of the entire recursion, it still returns to the same point from which the first invocation needs to return to. So a programming language that can recognize tail-end recursion would not be using additional stack space. Even though it looks recursive, it doesn't use up additional stack space. So it's kind of a weird thing, exception to the rule kind of thing. Yep. Alrighty. So I'm gonna stay online, but not, and I'm gonna turn off the voice channel because it is my office hour. Oh, that is cool. Kevin Hobbs. Alrighty. So I'm gonna get out of the voice channel now, and you guys have a good day. I'll see you guys on Wednesday.